Thanks, Vaivai. Good afternoon. I'm Mahesh Balakrishnan, and I'm going to talk today about Tango, which is a system we built over the last couple of years at Microsoft Research. So a common design pattern in distributed systems is to distribute data but centralize metadata. So in many distributed systems, you often have a centralized metadata component. This could be a scheduler for a MapReduce runtime. It could be a name node for a distributed file system, or it could even be a controller for a software-defined network. Now, if you have a centralized component at the core of your system, you have a single point of failure, and that's a problem. But the usual rationale is that you can always go back and fix this. You can harden it. You can make it highly available. And arguably, this is good engineering practice. Everybody does it. But this approach overlooks one significant problem, and that is that hardening an existing centralized service, making it highly available, can be very difficult. Often it requires you to rewrite your entire code. The key reason for this is that centralized services look very different from highly available services. So if you look at an example centralized service, you'll find usually that it's a very simple RPC server. It's receiving requests over the network, and it's manipulating state stored in in-memory data structures. Think Java or C# collections. Now, usually the service requires transactional access to these data structures. That's why it's centralized in the first place. And more often than not, developers tend to use simple locking because it's a centralized service. Now, this is what a centralized service looks like. It uses in-memory data structures. But if you look at highly available services, you find that the abstractions are very different. So you really have three options if you're trying to make a service highly available. The first option is that you use an external service like Zookeeper. And this has two problems. The first is you need to rewrite your code to store state in Zookeeper instead of your in-memory Java collections. And the second problem is that Zookeeper is essentially a particular data structure with a very specific API. And so it can be difficult, inefficient, or even impossible to emulate other data structures over the Zookeeper API. Your other two options are not very good either. You can use a Paxos library directly, but that requires you to rewrite your program as a state machine that's receiving upcalls from the Paxos library. And third, you can use your own replication protocol, and that can be very difficult to get right. Now, the goal of Tango is to bridge this abstraction gap. We want to let developers write centralized metadata services, using in-memory data structures, and we want to give them high availability without requiring them to rewrite all their code. So how do we do this? Tango provides the abstraction of an in-memory data structure backed by a shared log. So a Tango object has two components. It consists of an in-memory view, which is just a data structure on the client, and a history, which is an ordered sequence of updates that lives in the shared log. Now, the shared log is a magical entity. It's scalable, fault-tolerant, persistent, and it resides across the network. And later in the talk, I'll tell you how we realize such a shared log. Now, the way this works is when a Tango client wants to update the object, the Tango runtime, which is a client-side library, commits an update to the shared log and then modifies the local view. The central thesis of this talk is this simple design gives you a number of properties that are very difficult to achieve in a traditional distributed system. The first of these properties is persistence. So obviously, this design gives you persistence. If the client goes down, it can come back up and reconstruct its local view using the history in the shared log. So in a sense, the view is soft state, and the shared log contains the real state of the object. It also gives you availability. And we achieve this simply by having multiple views of the same object on different machines. So when the application on a particular client does any kind of an accessor operation on an object, the Tango runtime ends up synchronizing the state of the view with the history in the shared log. And doing this, we get linearizability, even though you have multiple views of the object. The third property you get is elasticity. You can bring up new instances of your service on new machines, and they can construct the local view simply by playing the shared log without interacting with other clients. And lastly, you get transactional semantics. You can do transactions over your data structure and get atomicity and isolation. We get atomicity simply by having two types of entries in the log, uncommitted updates and commit records. This is an age-old technique for getting atomicity with a shared log. But we can also get isolation, and I'll show you how we do that later in the talk. And we get these properties across multiple data structures simply by storing all the data structures on the same shared log. So this is the basic design, and this is really the most important slide in the talk because it tells you what we do. And an important point here is that Tango is built entirely using simple append and read operations on the shared log abstraction. So Tango does not send any messages on its own, and in fact the clients never talk to each other. Now it's true that the shared log itself can be a distributed system that passes messages around, but that Tango is oblivious to that. In the rest of this talk, I'm going to focus on three aspects of the system. I'm going to show you that Tango objects are really easy to use. They look like Java or C# collections. I'm going to show you that you can build new Tango objects very easily using tens of lines of code. And I'm going to show you that despite having a shared log at the center of the system, serializing all activity in the system, we can still get excellent performance, and I'll tell you how we do that. So moving on to the first point, Tango objects are easy to use. They look like Java or C# collections, and the code you see here is just a, it's a simple code fragment that's accessing a map and mutating a list. So it looks exactly like the code you'd expect if you're working with something like Java collections. Now, how does this work under the hood? We offer linearizable semantics for operations, and the way we do this is, under the hood, the Tango runtime is maintaining a local view, and the local view is synchronized with the history up to some point. So in this example, the local view is slightly stale. It hasn't seen the next 3 updates in the shared log. Now, when the application executes an accessor operation on an object, so here we're doing a get on the map, the Tango runtime essentially plays the history forward and synchronizes the local view with the state of the log. Subsequently, when the application does a mutating operation, the Tango runtime deposits an update record in the log. So this is a very simple design, and it gives you linearizability for singleton operations, for puts and gets and so on. But here is where things get really interesting. We can do transactions. So we can take that code fragment I showed you in the previous slide, and we can put a big tx and an ntx around it, and now we get strict serializability for transactions over data structures. So what's going on under the hood now? Well, it's similar to what we saw before. You have a local view. It's synchronized up to some point in the log. But now we have this notion of an uncommitted update and a commit record. So the dark blue entry in the log is a commit record. Now, when the application executes begin_tx, the Tango runtime doesn't really do anything with the shared log. It just creates in-memory state. It creates an in-progress commit record. And while we're doing this, there can be other activity in the system. So the orange updates are, activity by other clients in the system that are appending to the shared log. And our client here is not aware of these updates yet. Now, when the application does an accessor operation on a data structure, recall that in the linearizable case on the previous slide, we were synchronizing the view with the shared state immediately. In the transaction case, when your code is running in a transactional context, we don't do this. Instead, we return the state of the view immediately. And what the Tango runtime does is it makes an annotation in the commit record. It updates the read set in the commit record, saying the application saw this version of the object. Where do we get the version number from? Well, we have a shared log at the bottom. It orders all updates, so we can use the shared log as a versioning mechanism. So essentially, the version of an object is the last update that modified it. Now, as we continue executing on this transaction, when a mutating operation occurs inside the transaction, we end up dumping an uncommitted update in the shared log. It won't be made visible by other clients yet. And finally, on ntx, this is where the action happens. The Tango runtime goes ahead, takes this in-progress commit record, and dumps it in the shared log. Now, note that the commit is a speculative commit. Just because we put the commit record in the shared log does not mean the transaction has committed. To decide whether the transaction should commit or not, the client plays the shared log forward, synchronizes its local views with the state, with the history in the shared log, and then it makes the commit abort decision based on the following question: has the data we read in the transaction changed since we read it? So in this example, if the orange updates touch the data structure we read, then we need to abort. Now, every client is playing the shared log at the same time, and they will all encounter this commit record, and they will all independently make this commit abort decision, but they will do it deterministically. So if one client decides to commit, you can be guaranteed that everyone will decide to commit. And this is essentially a scheme that we took from a database called Hyder that Phil Bernstein and a couple of his colleagues built. Now, we offer a suite of Tango objects to the application, Tango maps, Tango lists, and so on. But we also want to give developers, slightly more sophisticated developers, the ability to build new data structures, things like arbitrary priority queues and so on. And I'll walk you through this code. The high-level point here is 15 lines of code. We get a register that's persistent, transactional, highly available, and elastic. And so this code really has 4 components. It has some internal state. This is a register. It's the simplest possible Tango object, so the state is an integer. Second, it has an up call that the Tango runtime invokes whenever there's an update to be applied to the object. This is exactly equivalent to a state machine up call if you're familiar with that, state machine replication up call. Third, you have some set of mutator methods in the data structure. In the case of a register, it's a write. In the case of a map, it would be a put, and so on. And all this does is it serializes the update and gives it to Tango. And Tango ends up doing some sort of an append on the shared log, as I showed you in the previous slide. And finally, we have some set of accessor methods on the data structure. And depending on whether you're in a transactional context or not, this behaves differently, as I showed you before. If you're doing linearizable operations, this ends up synchronizing the local view before you access the state. If you're doing transactions, it just makes an annotation in the in-progress commit record. So this is what a Tango data structure looks like. And the interesting point is, this is a toy example, but we can build fairly sophisticated data structures using this template. So for example, a Java collection like a concurrent map is around 300, 350 lines of code. We can also implement systems like Zookeeper. So original Zookeeper is 13,000 plus lines of code. We can emulate that API in 1,000 lines, and we get transactions in the bargain. So I'm going to go to the third part of the talk, which is performance. We're sending all this data through a shared log. Isn't the shared log a bottleneck? So let me just go through the design as I've described it. Up on top, you have an application on the client. It's interacting with data structures, Tango data structures. Each Tango data structure is interacting with the Tango runtime, which in turn is doing appends and reads on a shared log. And the API that Tango needs is that it needs to append and read, obviously. It also needs to be able to trim entries in the shared log for garbage collection. And there is a check primitive that returns the current tail of the log. Now, how do we implement this? The secret is that we have a distributed implementation of a shared log called Corfu. We published this earlier in NSTI. And I'm going to give you a very quick high-level overview of it. In Corfu, every entry in this shared log, in the address space of the shared log, is mapped to a subset of storage nodes in a cluster of flash drives. So this has the property that every read on a different address is going to go to a different set of storage nodes, which means that the read throughput of the system scales linearly with the number of drives. There's no central bottleneck. The way that appends work on the shared log is that when a client wants to do an append, it goes to a centralized sequencer node, obtains a token. This token is essentially the next free location in the shared log. And then once it has the token, the client goes ahead and sends the update directly to the storage nodes. Now, you may look at this and think, hold on, the whole point of this was to make centralized services highly available, and yet at the bottom you have a centralized sequencer. What's going on? It turns out that we don't really need the sequencer for safety or liveness in this design. Multiple clients can guess where the tail is and keep making progress. We ensure safety in that case. The sequencer is sort of a contention manager. It just ensures that nodes don't contend on the tail of the log. So if it fails, we can reconstruct it. It has soft state. And really, it's a network counter, so we can run it very, very fast. We have an implementation that runs at 600,000 operations per second. So the big takeaway is we have a shared log implementation. It's very, very fast. But that's not enough. It turns out that when we actually build applications over this shared log, we hit a performance bottleneck very quickly. To give you an example, here are two services. Think of them as two schedulers that are sharing a free list. So they have their own data structures. Service 1 has data structure A, service 2 has data structure B, and then they're sharing a free list C. Now the problem is, as I described Tango, all activity is going to go into the shared log, and each client is going to play the entire shared log. So service 1 is going to see updates belonging to B, service 2 is going to see updates belonging to A, even though they don't care about these data structures. So the way we get around this, what we call the playback bottleneck, is that we introduce a streaming abstraction. Every object gets its own stream, and we implement an interface where the client can say, give me the next entry belonging to this stream. So each client in the system only plays the subset of traffic that it's interested in. And as a side note, we allow entries to belong to multiple streams because that's how we do atomic updates now, if you want to modify multiple data structures atomically. So this is good. It sort of reduces the scalability bottleneck, but we still have a problem. The transactional scheme I talked about doesn't really work in this new setting anymore. So this is the example from the previous slide. I'm just looking at service 1 now. And service 1 is doing a transaction. It's reading A and it's writing to C. And so the transaction protocol is going to work exactly as before. Now note that service 1 will not see updates belonging to B because of the stream abstraction. So it goes ahead and it puts a commit record in the log. And all clients running service 1 will encounter this commit record and make the commit decision deterministically. So this transaction commits if A has not changed since we read it. The problem we have now is that service 2 knows nothing about A, but it does care about the free list C, so it's going to see this commit record in the log, but it can't decide whether the commit should happen or not, because the commit happens if A hasn't changed, and service 2 does not know anything about A. So how do we get around this? Well, service 1 helps service 2 out. Service 1, after it makes the determination that it should be a commit or not, it introduces a decision record into the log, which is just a deterministic bit. It's 1 if it's commit and 0 if it's abort. And service 2, when it encounters a commit record that it can't resolve, just waits for the subsequent decision record. So I'm going to move on to evaluation. And the evaluation setup is very simple. We have 18 clients, 18 Tango clients. They're running against a Corfu deployment. The Corfu deployment has varying number of log servers. And so in this case, there are only 2 servers in the log. And it's doing two-way replication. Every update goes to 2 log servers. The Corfu sequencer is running on a 32-core machine off to the side. So the first experiment we are doing non-transactional linearizable operations on a Tango register, on a single data structure. In the background, we have 10,000 writes per second going to this register, irrespective of the number of clients. And we're adding read-only clients to the system because we want to scale the read throughput of this register. So you can see that as we add clients, each client is adding 10,000 reads per second, strongly consistent reads to the register. At some point, we flatline, and there's essentially a bottleneck. The shared log is saturated. If we beef up the shared log by adding more servers to it, we keep scaling. And we keep scaling until at some point the shared log is again saturated. So the point of this graph is very simple. We get elasticity for strongly consistent reads. That's a property that very few systems have, none that I know of. Usually you can do elasticity for stale reads. We can do it for strongly consistent reads. Now, I'm not going to lie. There is a bottleneck, but that bottleneck is in the millions of operations. So this shows linearizable operation performance. What about transactions? So this is a very similar graph. Again, we're adding clients on the x-axis. But here we're doing read-write transactions. So each client is doing a read-write transaction on a Tango map. It's reading 3 keys and writing 3 keys. And here you can see, again, it's a very similar kind of graph. More clients is more throughput. At some point, the shared log is saturated. And the point here is this almost looks like the graph for a conventionally partitioned system where you have independent partitions. Each client has its own Tango map. No transactions are crossing boundaries. But we have a cap on throughput. And again, we can lift the cap. We can add more log servers, and the cap goes into the millions of operations. But you'd be a fair question here would be, hold on, I could have gotten this performance with a conventionally partitioned system. Why am I suffering this cap on aggregate throughput? Well, the reason is that we can do transactions across objects. So I'm going to focus on one particular data point here, which is the one where you have 18 clients. Each client has its own Tango map. In this graph, they're all doing independent operations within the partition. In this graph, I'm going to change the number of cross-partition transactions. So now you have 18 clients, 18 Tango maps, but now they're doing operations that span other clients' Tango maps, what you'd call a distributed transaction. And here you can see that as you increase the degree of cross-partition activity, performance goes down, but it goes down very gracefully. So even when 16% of the transactions are crossing partitions, you still get 100,000 transactions per second. And as a sanity check, we decided to just compare this against something like two-phase locking, which is a conventional distributed protocol. And we find that we get very similar scaling properties. The important point to note here is that we get these properties without suffering all the problems of a conventional distributed protocol. We don't have to worry about deadlocks, clients crashing, holding the lock, and so on. So I'm going to conclude by reiterating what I told you. A Tango data structure is a very simple abstraction. It's a data structure backed by a shared log. And the key idea, the one takeaway point of this talk is the shared log abstraction is very useful. We can make it do all the heavy lifting, all the things that are very difficult to do in a distributed system. And the three things I showed you were that Tango objects are very easy to use. They look like Java or C# collections. So from the programmer's point of view, all you have to do is create a Tango map instead of a Java map. They're very easy to build. In tens or hundreds of lines of code, you can create new data structures with the exact properties you want. And they're blazingly fast because we have a very fast shared log, and then we have this notion of selective playback using streaming, and that lets us remove the bottlenecks in the stack. And finally, I'd just like to point out that we really want Tango to occupy, to play a role for metadata that MapReduce has for big data. We want to make it easy to build such systems, and it really shouldn't be a black art to build a centralized metadata service that's highly available. Thank you.
Questions submitted on the moderator. Okay.
I have a question. You say that when you recover something, you go back and you replay the history. How far do you have to go back?
So that's a good question. There is no magic here. I mean, the way you recover from a log, if you want to do it faster, you have to checkpoint. So you have some trade-off between checkpointing and how much state you remove from the log. The interesting point is that Tango itself provides you with some framework for checkpointing. So you can create a checkpoint stream and a data stream for the same object. So we sort of make things simpler, but there's no magic there. You do have to create checkpoints if you want fast recovery.
Usually in traditional databases, you have to take some kind of a periodic dump. If it's a sharp dump, you had to freeze everything.
Oh, we don't need
If
to
it's
do
a
that.
fuzzy dump, then you can roll through it.
So the fact that we have a global ordering over all updates in the log, something I didn't talk about in this talk, is that you can recreate the state of the system at any point in time simply by playing the appropriate prefix of the log. So taking a checkpoint would mean you play the prefix of the log, you have the state, and then you just write the state back out, and you trim all the entries before. So it's a lot easier for us to take a checkpoint. And the other capabilities you'll get, like geo-replicated asynchronous playback. If you want a mirror of your system, all you have to do is play the log asynchronously on a different replica.
Yeah, so this is really awesome. Can you tell us a little bit about the synchronization issues that arise? I mean, you didn't say anything about locking, but obviously if you have contending transactions of this sort, how are you guys handling that?
So the contending, we're doing optimistic concurrency control. So there's no locking involved. And essentially, whoever gets to the shared log first wins, in a certain sense. If two clients are trying to do, modify the, doing a conflicting transaction, they're going to race to the log. One of them is going to win. The one who gets there first essentially wins, and the other one backs off and retries.
So traditionally, that would start to have high abort rates. And so do you have a plan for how you're going to deal with that?
I think the short answer would be no. The key point here is the size of the conflict window is critical here. So the latency it takes us to append an operation to the log is critical. And in the systems we're building, we have append latencies of maybe 2 milliseconds, and that is probably too high to do conventional, database workloads. But it's okay for things like key-value stores if you don't have too much of a skew. We're trying to narrow that down. I mean, if you had things like 10 microsecond RPCs, then maybe you can get the conflict window very small.
So there's one question from the moderator. Basically, the question is that you say the next bottleneck isn't until the coordinator are the meanings of operations, but the evaluation slides only show scaling going a little past the first bottleneck. Do you have evidence of where the next bottleneck actually arrives?
So it's a very simple analytical formula. I mean, the sequencer of the bottleneck, it can do 600,000 operations per second. If you don't do any form of batching, that directly translates into the number of transactions you can do. If you do batching, which all systems do in this space, you can end up scaling that to maybe a few million operations per second. It's really a function of the batch size, times the throughput you get from the sequencer. Yes.
Mark. Mark Lillibridge from HP Labs. What happens to the performance when you replicate across data centers so you can survive a data center hit?
We don't know. We haven't tried it at all. We don't have a geo-replication story really for this at this point.
All right, thanks, speaker.